Well, this lecture, its result is going to be the theorem on the number of sign changes, which is kind of strange, but it continues with the previous lecture. And we will have an example that is germane to that previous lecture as well. And so let's look at the theory on sign changes. Say that we have some continuous function w that is positive, and suppose that we have a continuous function f that is not identically 0, and suppose that this f is w orthogonal to the set of polynomials of degree at most pi, at most n, then f changes signs at least n plus 1 times on the open interval ab. Okay. And this is going to be an application of the stuff we've been talking about. So let's take a look. Okay, first we're going to note that 1 is in pi sub n. It's a polynomial of degree at most n. And notice that that then 0 is equal to f inner product of 1 is equal to the integral from a to b of fw by the definition of inner product. Again, because this is because we're saying f is w orthogonal to pi sub n. Now, since f is not identically 0, there has to be an interval wherein f is positive and an interval wherein f is negative. Okay, so it's going to have to change signs at least once. Okay, so let's say that it changes signs r times, and to get a contradiction that r is less than or equal to n. Okay, so choose numbers t0 through tr that are strictly increasing so that f has the same sign throughout ti to ti plus 1. Okay, and so it's going to be, well, anyway, so it's the same sign throughout these. So now, from those choices of t, okay, construct a polynomial p of x as to be x minus t0, x minus t1 up through x minus tr. This polynomial is going to have the same sign throughout each of these intervals as well. Okay, now we multiply f of x and p of x, and since each of them has constant signs throughout those intervals, that product is either always positive or always negative. Okay. Therefore, since the degree of p is less than n, I mean less than or equal to n, it's equal to r, right? We can take the inner product of f with p. Okay, we can calculate it, and that's not 0 because this is either always positive or always negative. W is always positive, so this guy is not going to be 0. Therefore, this inner product is 0. But since the degree of p is less than or equal to n, this contradicts our assumption on f. Okay, so this is a cool theorem to study. Okay, it's not that difficult, but it's clever. Someone was careful and noticed things, and this is nicely organized. Okay. Now, we've been talking about these polynomials that are orthogonal. Let's kind of look at some. First, I want to start out with just notice something. The integral from -1 to 1 of x to the nth power dx, that'll be 0 when n is odd, and it'll be equal to 2 over n plus 1 when n is even. Okay? This is Calc 1. All right. Now consider this polynomial q of x squared minus 1/3. Let's take the inner product with 1. And whereas, okay, I know we define the inner product as an integral, don't compute it as an integral unless you absolutely have to. Okay, the idea with this notation is that you compute a few specific values, and then you let the structure of the inner product do the rest of the work for you. And so by this I mean I take my polynomial q here and 1 here. I use the properties of the inner product to simplify it, and then I apply this one calculation above for this part and this part. I do my arithmetic and it's equal to 0, and I only have this one integral, which is easy. Okay, and so this is the point of developing this type of notation. Okay, now all of that having said, this q is orthogonal to 1. Okay, so take that, put it in your pocket. Okay, now let's take this q and do an inner product of q with x, and we do the same as we did before. Use the product to simplify, and let's say, gosh, with this inner product I can take this x and move it across the comma, make that an x cubed minus 1, so this is 0, and because this is odd, this is 0 since this is odd, so this is 0. So therefore q is orthogonal to x. Okay, so therefore I can say that q is orthogonal to pi 1, okay, which is spanned by 1x. Okay, now note that x squared minus 1/3 is 0. Set that equal to 0. So this polynomial q has roots plus or minus 1 over the square root of 3. Okay, put alpha equal to 1 over the square root of 3. So therefore, going back to my Gaussian quadrature, I can just evaluate this integral by plugging in at this point and this point. Plug in at the roots. There you have it. How does this work out? Well, let's see. Oh, well, my integral is equal to 2. Okay. Well, anyway, so it works. I need to figure out what A1 and A2 are. Okay, this is what it is, but I need to figure out what A1 and A2 are. Okay, and so I know what the integral from -1 to 1 is. It's 2. I get A0 plus A1 is equal to 2. I know what the integral from -1 to 1 of x is. It's 0. Okay, so I can figure out that A1 minus A0 minus A1 is equal to 0. So A1 is equal to A2. Substitute this back into here, and it gives me that they're both equal to 1. Therefore, I can integrate my function just by evaluating f, at negative alpha and at alpha. I mean, how much easier could it be than this? Because the coefficients turn out to be equal to 1. Well, so I can go through a change of variables, okay, and doing so I can get the integral from a to b of f of x to be approximated by one of these should be an approximate here, and for this. And anyway, this should be exact for any f element of pi sub 3. So let's check it out. If we do my integral for 0 to 1 of x cubed, again going through this change of variable process, I get 1/2 times, negative alpha plus 1 over 2 cubed, alpha plus 1 over 2 cubed, and bang, dead on accurate right there. Okay, the Gaussian quadrature, it's awesome. All you have to do is figure these out once, okay, just once, and then you get to integrate again and again and again.